I think it's time to start. As the Romans say, tarde venintibus ossa. So our first speaker is Mr. Priyadarshanam. You are welcome. 10 minutes.
Good morning. My name is Priyadarshan. I'm from the Indian Institute of Space Science and Technology, Associate Professor in the Avionics Department. So I would like to first thank the UNOOSA and then Samara University for inviting me here to deliver this talk. So before I would like to introduce briefly our institute. It comes directly under the Department of Space. Under the Department of Space, we have three main divisions. The Indian Space Research Organization with all its allied centers. And then we have a commercial wing, Antrix. And then there are a set of research institutions which carry out the research activities. So IIST is a recently established institution of education. It was established in 2007. So it's the only institute catering to the space in India, the research educational aspects of it. It's an university established in 2007. So mainly to create a learning environment enriched by the challenges in the space program. So in addition to that, the other mission is to promote activities to address social needs and of course network with national and international institutions. So this is the proposed institution map, the layout. So one wing, the academic wing with the hostels are almost completed. So the other wing, which has accommodations for the faculty members and then the gymnasium and other things, are under construction still. So it's still an ongoing process. So our institution mainly offers four main programs: the undergraduate degree, the master degree, the dual degree program, and then the doctoral and postdoctoral research. So we have three main departments offering the undergraduate degrees: the avionics, the aerospace engineering, and the physics. The rest of the departments offer only the postgraduate degrees. That's the master degrees. The bachelor degree is a 4-year program, the usual 4-year program. Admission is through All India Joint Entrance Examination. Around 1.3 million took the exams in 2017, this year. And out of that, 20,000 qualified, but we have the capacity for only 140. So it's a very small institution of approximately 1,000 students. So in the avionics area, we take around 60, aerospace 60 students per year, and then the engineering physics is a dual degree. This is master plus, bachelor's plus the master, around 20. So we have around 15 master degree programs. The avionics department itself offers around 5, control systems, signal processing, and other things. And then the aerospace engineering offers aerodynamics and flight dynamics, structures, and then thermals and propulsion. And then the rest of the departments also offer a few master degree programs. So we have around 100 research scholars. So that is a brief introduction about our institute. I will just talk about the satellite related activities or the space related activities which are happening in our institute. So mainly the satellite program in our institute is to set a small satellite standard for the Indian education institutions and also to provide hands-on experience on design, fabrication and realization of small satellites and also subsystems. So the mentorship is provided by the Indian Space Research Organization and of course the IIST faculties themselves. Our aim is to have a continuous activity for developing and launching small satellites as well as some payloads for the interplanetary missions. So currently we are having a few programs, like we have our own Nano-satellite program which was initiated recently. Then we have a collaborative activity with for international institutes. One of them is the Inspire Sat-1. I will briefly discuss about them. And then we have an RST mission. Then we have proposed a retarding potential analyzer as a payload for the Indian Mars Orbiter mission 2. And then we are establishing our own ground station for the applications, for the small satellite applications. So we have also proposed similar payload for the Venus mission. And then we are carrying out various small technology demonstration activities for the small satellites. So I won't go into the details of the technical things of the satellite. We have collaborative activity with Laboratory of Atmospheric and Space Physics, University of Colorado Boulder, which is called the Inspire Sat-1, then National Central University Taiwan, and then Indian, of course, we are there. Professor Mike McGrath is here. He had visited us a few times to deliver workshop on the mission, small satellites. So the collaborative activity mainly includes this thing. The payload is developed by the National Central University Taiwan, and then the communication system by the Taiwan, then command and data handling software, the power systems by IAST, and then the structures and of course the control system by Laboratory of Atmospheric and Space Physics. So we can see clearly that multiple institutions across the continents are coming together to build this satellite. I will share some experiences on working in this collaborative way. So we are also working on an autonomous assembly of reconfigurable space telescope mission with Caltech University and JPL, United States of America, then University of Surrey, and then of course we are here. A brief description. So instead of launching a huge, probably if you are looking at 30-meter telescope in future in the space, it's not possible to launch it in one go. So the aim of this is to demonstrate that we can launch independent telescopes which are deformable, and then they can assemble in the space and then form a big mirror. So in order to demonstrate this, we are going to demonstrate using only a small spacecraft which can be made by the students. So the mass is around 40 kilos, and we can see multiple mirror segments. Some of them are rigid mirror segments, some of them are deformable, and then these mirror segments reflect into this camera to capture the image. So this is a compact configuration. So we have to demonstrate that these two mirrors separate and then reconfigure at a different location, and then demonstrate that the mirror deformation is possible, and then it can capture the images accordingly. So this will effectively demonstrate that we can carry out such experiments in future with possibly larger satellites, independent satellites carrying the mirrors. So IAST IAST's involvement is in building one of these mirror satellites, except for the payload. Sorry, the payload means the mirror itself. We will build one satellite. University of Surrey will build one satellite, and one of the satellites will be built by the Caltech University. So we have also proposed retarding potential analyzer for the Mars Orbiter 2 mission, which will be launched in next few years by ISRO. So these are some of the subsystems developed by our students, mainly the undergraduate students. We have developed multiple versions of onboard computer based on different processors, one on DSP processor, one on the usual ARM processor, and then the recent one with FPGA and ARM processor sitting on the same core. This is the most recent motherboard we have created for the ARM processor, FPGA based ARM processor for the Inspire Satellite 1 mission. So we have the DC-DC converters for the small satellite made by the students once again, and then the control systems board right now it is based only on the magnetotorquers. We are also working on the one with reaction wheels. So these are some of the setups created to test. This is an Helmholtz coil to test the small satellite under the magnetic influence. So the students have also built a test setup for based on the air bearing for reaction wheel systems to carry out to test the control algorithms. Okay, so that's about briefly the activities we are having, and I will now share some of the experiences and how many students have been involved in this. So what we notice is approximately we started in 2011 with very few students, 3 in the 4th year. So usually in the 4th year of the undergraduate degree they take up the project works, and then some of the project works are to create these subsystems. So then in 2014 we thought that we should include students from earlier semesters also. So when we started including them, we saw a slightly improved work. However, we noticed that there is a exponential decay in their interest. So we have a large number of students showing interest in the beginning, and then you can see the rapid decrease there. So this is one of our experiences. We have to address this issue if we have to have a consistent workforce. So these are some of the challenges we have faced. So it is very difficult to retain the students to continuously work from the beginning of the semesters up to the end of the year. So currently most of our work is done by the undergraduate students. One of the difficulties is the student currently it is only an voluntary work. We do not force them to take up the credits or not. We don't have credit for that. Basically we don't have no credit for working in the satellite project. So whatever we have carried out now is completely voluntary. So schedules are impossible to meet as of now. So they have very short duration, semester duration time of around 4 months, and within that they have some 3 exams. So we cannot extract any work during their examination. So effectively approximately 45 days or something is what we get out of them in every semester. So we have also noticed that they are able to, the students are able to do concept products, but not the finished products which can fly. So this is one of our experiences. So further the other challenges are we have faculty members who are not experienced in the space products. So all of the faculty members in our institutes are from the standard academic institutions. They have no prior experience working in the space products. So the space research, Indian Space Research Organization engineers are willing to help, but it's very difficult to get their time. I think it must be similar with Roscosmos also. We have poor manufacturing support from the local industry. Indian manufacturing industry is still under revive. So funding was an issue until recently, but things are significantly improving now. Fund is not the major problem for us, but the rest of the problem. So yeah, what we think is maybe should we think of a new curriculum based on these experiences. This is what is at the back of our mind. So we are under discussion with University of Colorado. There is a Laboratory of Atmospheric and Safe Physics to see if we can come up effectively with some kind of courseworks. They have a spacecraft design course which runs in their department. So we do not know whether it should be an undergraduate or higher education. If it is undergraduate, the students are there for 4 years. We may be able to tap their experiences, but the coursework has to be significantly modularized to satisfy satellite creation or whatever, space products. But however, one of the difficulties would be what will they do after graduating? This question, currently Indian space industry, only the Indian Space Research Organization is the only one which provides employment directly to the people experienced in this area. We do not have any private industry significantly to take these students after they complete the degree. So that is one of the issue. So working with Inspire was very helpful to us. What we saw was when we put different people from different countries together in the same location, they have it helps in cross-cultural exchange of thoughts and ideas. And we also saw that the work progress was significantly high. So student exchanges has greatly increased the enthusiasm among the students of our institute. I think this is a right way to do. It's my opinion. Of course, how to go ahead? We believe that the faculties require training in the space area. So this creates a permanent resource in the institute. Instead of training the students who do not come back and directly contribute to the institutions, we should have a long-term training mechanisms for the institutes which are willing to work in this space area. Of course, we require regular student exchanges to boost their energy levels. And then we believe that setting up credit courses will also help to increase the speed. Of course, I have some minimal suggestions. So we believe that continued support for travel and hospitality for the candidates from third world country, to include long-term training. I think this is the one which will significantly help to the faculty member mainly, because once the faculty member is trained and when they go back to the institutions, they will be able to create new engineers in the same area. Maybe I do not know how feasible the second one is. We have to discuss with all the spacefaring nations to convince them to provide free launch facility for the university satellites. I know it's difficult, but still, probably if the university satellites are in collaboration with the local university, maybe they will agree. Of course, it will also be helpful to establish regional university centers for the UNOOSA activities. And I would offer IIST would like to be one of the centers, university centers for the future in India. Final slide. We have to develop an international small spacecraft standard so that multiple universities across the countries can work on these subsystems in parallel. And then each subsystem need not be, every subsystem need not be created by every university. Only certain things can be done in each location. And then each university can develop an expertise in a specific subsystem. That is my belief. And then, of course, it's going to significantly reduce the cost. That's all. Thank you.
Thank you. Does anybody have any questions? Please.
Thank you for the presentation. This is not a question, it's a comment. You said you would like to be UNOOSA University Center. Yesterday, Laurent talked about Capacity Building Network, CBN. So that's the mechanism you should use. That the CBN is being created to accommodate things like that. Thank you.
Thank you.
Well, it's quite similar, but I think it will take quite a few times for United Nations to create such the organization mechanism. But we have UNISEC, the global mechanism, and you can join if you wish.
Sure. Thank you. I will.
So no replies?
Yes.
Okay, thank you very much. So next speaker is Mr. Sanat. You're welcome.
Well, good morning. Dobre utra.
Microphone, please.
Oh. Well, the title is pretty long. That's Acquisition of National Capacity in Space Technology and its Concurrent Applications in National Development. Of course, I'm talking about the experience of Sri Lanka as a developing nation. So I thought this would be pretty much pertinent because these are dual challenges that any similarly circumstanced nation is likely to be faced with. So on the one hand, your technology base has not matured, so you need to work with them. We need to continually work to bring it up to a mature stage, and at the same time, then you are under pressure to apply, space technologies for national development activities. So this, how we have been trying to do that. So I'm sure that this experience would be shared by some of the similarly circumstanced nations as well. For those who don't know where Sri Lanka is, that's in the middle of the Indian Ocean, just below the Indian subcontinent, just above the equator. And our southern neighbor is Antarctica. So this is a location which is very advantageous when it comes to positioning of satellite ground stations as well for Earth observation data, which has been actually identified a couple of big players. The country's size is about 65,000 square kilometers, and we have 21 million people, and a GDP of just 81 billion, but that's just below the upper middle income country status level when you look at the per capita GDP. And Sri Lanka ranks pretty high on the Human Development Index. We are in the high Human Development Index category, ranking 73 out of 188 countries. So when it comes to policy level, the role of science and technology in general, so this applies to space technologies as well. So this has been pretty well aligned to national development agenda at the policy level. So, sustainable development goals are pretty much enshrined in all relevant national development goals, and of course, it's obviously it's working towards sustainable economic growth while ensuring environmental sustainability, save the planet, and social equity, leave no one behind. So we have come to understand our economic growth rationale after having been progressed to just below the upper middle income status level, so that as a nation we can't be depending on more and more use of factors of production for increased growth. So we have exhausted that stage. So therefore, definitely future growth has to be innovation driven. So the economic growth model is going to be an innovation driven knowledge based economy. So this is where space becomes pretty relevant. So our national policy development framework has identified those areas as areas of advanced technology where major investment needs to be done in order to ensure this economic transformation. So you can see space technologies and applications are pretty much high there on the agenda when it comes to the areas of investment identified for economic transformation. So that means at the policy level, it has been given very, due recognition. Then, what is the problem? What are the challenges for space technology capacity development? One of the problems that we see is that capacity development approach is currently largely characterized by technology push on the part of technology development agencies. There's agencies like us. In fact, the agency that I represent is supposed to be the space agency in the making for Sri Lanka. We don't have an entity called a National Space Agency, but we are supposed to be building towards that direction in addition to in addition to functioning as a public research institution specialized in space, electronics, telecommunications, IT, and robotics. So we have this special mandate to work towards development as the future national space agency of the country. So, so it is being pushed by agencies like us rather than the user community, potential users and prospective users of space technology applications putting up sufficient demand. So there's a significant awareness gap even on the part of potential major user agencies. Let it be in the area of agriculture, irrigation, water resources, natural resources management, coastal conservation. Even in some of those major areas, there seem to be significant awareness gaps about the potential of technology in harnessing its potential for national development goals. So, and there is a major awareness gap at the levels of strategic management in those organizations. Unless the leaders are fully aware of the potential, as we all know, less and less resources would be allocated to those areas. There won't be adequate funding. So advancing the course of national capacity development in space technologies and applications remains a job for the technology community without significant involvement of the user community. So I think this is a situation that can be seen, as I said, in most of the similarly circumstanced nations, I guess, because it's the technology development agencies which will have to do this technology drive, promotion drive, while the potential users are still not fully aware of the potential of harnessing those technologies for specific domains of application. So one of the biggest problems is developing the critical mass of human resources necessary in this area. Actually, when it comes to development of critical mass of human resources, it's common for both technology users, potential technology users, as well as the technology developers and promoters. As far as the technology users are concerned, areas like remote sensing, geographic information systems, GNSS. Of course, we do have some good quality university programs at the master's level conducted by some national universities, and then there are training programs that are conducted by institutions like us. But the problem is the numbers are inadequate in order to bring it up to that critical mass that will be necessary for effective application of those technologies in the respective domains of application. But when it comes to the technology developers side or technology promoters side, the institutions like us, the opportunity is available for advanced training outside the country, particularly advanced specialized training in specialized subjects, is not adequate for the engineers and scientists who are working in technology development agencies like us. So this is a problem that still needs to be addressed. So what is our roadmap for space technology capacity development? We have three strategic elements. One is, of course, establishment of a national hub for receiving and distribution of Earth observation data. I'll describe that later. An acquisition of basic space technology capabilities through a nano-satellite development program, and then domain-specific collaborative research on space technology applications with those domain agencies. So these three initiatives are undertaken by the Arthur C. Clarke Institute for Modern Technologies, the public institution that I am coming from, which I said is the National Space Agency in the making. So this is a proposed national hub for receiving and distribution of Earth observation data. The antennas are not yet there, so this is what we want to establish. So this is going to happen in the future, so we hope we can start work towards the end of this year or beginning of next year. So some contour maps that we have identified in the site. And this is a second initiative. So this one actually is meant for ensuring that we have enough satellite data obtained on a regular basis, which will be needed by all our use agencies, whether they are in agriculture, environmental management, weather and climate, then ocean resources management, urban development, transportation, all these areas, the satellite data that we need, we hope to obtain through international global Earth observation satellite systems. So, and for capacity development in the area of space technologies, we have embarked upon a Nano-satellite development program. And here we have two initiatives. Actually, this is planned by our institution once again. So it is intended to develop national capacity in space technologies and applications, and then at the same time developing systems engineering capabilities. You find that we have those capabilities scattered in our institution as well as the other institutions. So this will be a project to bring up those systems, bring up all those multiple expertise in multiple disciplines, and to bring them together to develop systems engineering capabilities. So here, these are the objectives, basically. And we have started this with the, I'm very proud to say, with the Samara National Research University. We started the inaugural planning workshop. We did that in August last year, and the project is now progressing. These are some pictures from Sri Lanka with Dr. Igor Belokanov and his team there in Sri Lanka last time. So we are following this. Of course, we sent a team of 17 engineers to Samara National Research University for a 1-month training, and we are continually working through distance learning, and of course we are making very good progress with this project. And we have another initiative that is, of course, with the QTech Institute. So 2 of our research engineers are there building a 1-unit nano-satellite under the BIRDS 3 program. So unfortunately, their picture is not here. So this is from BIRDS 1 and 2 groups. So we see our colleague George Maida. And then as for domain-specific collaborative research on space technology applications, we have started this project under the United Nations Economic and Social Commission for Asia and the Pacific, the only United Nations Commission which is having a regional space applications program. So it has this agricultural drought monitoring and early warning project, of course use of space applications for this area. So we are working as one of the first pilot countries on this, and we are carrying out this project. This is a multi-year project where the models that we are developing have to be verified after ground truth validation. So on the top you see, I mean, this part of course I would say capacity building as well, though. So making the top level aware, there are 2 cabinet ministers and 2 secretaries to the ministry, 2 ministries, agriculture and science and technology on the top photograph. So this we have thought is very important part of awareness building. So we have done that. That's how we have been able to, ensure that this is reflected at the national policy agenda. So some of the pictures showing NDVI, Normalized Difference Vegetation Index, which is one of the parameters that is being used for agricultural drought monitoring. These are data from AWIFS sensor, and some work that has been completed. So these are some. Then we also have some domain-specific research with other agencies in those areas: agriculture, environmental management, natural resources management, irrigation, ocean resources management, urban development, public health, etc. And we're also supporting, complementing this with UAV and also with spectroradiometry by developing a spectral signature bank and a spectral radiometer laboratory. So these are some of the international, these are some of the platforms, international and regional platforms where we get some capacity building support. Of course, UNESCAP RESAP I mentioned, then the Center for Space Science and Technology Education in Asia and Pacific. Of course, this is in India, and we are also hoping to build strong relationships with the Chinese center as well. The UNOOSA, APRSF, and HIST is an international center for space applications on cultural and natural heritage. Of course, then we have this inter-agency relationships with Samara National Research University, ISRO India, RADI China, and QTech. So the interventions have been basically in these forms: postgraduate training, short-term specialized training for experts, expert missions, collaborative research, and technical assistance. Well, I think this is all what I can share within this time. Thank you very much.
Thank you. Any questions, please? I think no questions are present. Thank you again. And it is likely my turn, so I'm going to pass the floor to myself. Oh, a question, sorry.
I wanted to say I think you're doing something very interesting, but a question having to do with the reception of the idea at the highest levels of government. What are you finding to be the challenges at this point? Or are the high-level cabinet ministers thrilled with this opportunity, or are there challenges that you face?
Well, I think this is what I mentioned in one of the slides. Of course, we have been wading our way through, and as we have been very aggressive, it has been possible for us to bring it to the highest political agenda, highest policy level agenda of the government. But unfortunately, as the user agencies, as far as the user agencies are concerned, there is a bit of lack of awareness, even at the top levels of those user agencies. That is, CEOs of those user agencies perhaps do not fully appreciate the potential of space-derived data, tools, applications, so forth and so on. So this is part of our capacity building efforts. We are also conducting a regular CEOs forum, that is Chief Executive Officers Forum for user agencies of, potential user agencies of space technology applications like remote sensing, GIS, and GNSS. That's how we are trying to bridge that gap.
So, dear colleagues, my name is Ilya Kudryavtsev. I am Dean of the Faculty of Electronics and Instrumentation. So I would like to discuss some issues about GNSS technologies. GNSS was already mentioned here, and it is likely interesting for several countries, for several space programs. Just to remind, the acronym GNSS stands for Global Navigation Satellite Systems. Actually, we have been teaching students to this program since 2014. And here you can see the head of this program, Professor Kai Bohrer. Typically, if you want to establish a world-class program, master's program, or any other program, you should have somebody like him. Kai Bohrer is a worldwide known expert in GNSS. He was working with GNSS from the very beginning of this technology. And it is a great fortune of us to manage to persuade him to come to Samara and establish this program using his great experience in the United States, in Denmark, and so on. The group was established from the very beginning as an international one, and it is an English-speaking program. You can see here that we have very different students, and also our staff is also international, from the United Kingdom, from Denmark, and so on. Actually, our university is a member of Russian program, so we are funded by our Ministry of Education to get 100 of the best universities in the world. So these are our goals which we set for our program. So we want a world-class level of education. This program is supposed to contribute to the reputation of the institute and our university in general. And another task is to attract foreign students in order to raise some indicator values and to increase the level of our teaching and education. Actually, one of the most effective instruments to raise the quality of education is internationalization. Internationalization is a complicated process, and it includes foreign students, foreign staff, actually international curricula, and so on. So we just followed this recipe, which was successful for many leading institutions throughout the world. And definitely it is necessary to create a research laboratory, because our motto is education through research. When you teach some engineering tasks or fundamental tasks, you should always think about it. Several objectives, you can see them here. So the idea is more or less the same. We created international groups of students. We invited international staff. And we hope that all these activities provided good opportunities for our students. About learning. GNSS is a very complicated task. Many people think that using GNSS is just press some buttons on their smartphones. No, it is much more complicated. Our students are supposed to be able to create their own GNSS receivers, multi-system, multi-frequency receivers, and they are supposed to use all these complicated technologies for their specific tasks. So this means that we have to create high-quality curriculum, and we should create all the conditions for their growth. You can see here our ideas. I think it is not necessary to read them. Actually, students are very active typically, and they try to create their own devices, their own algorithms, as well as study the courses. Here you can see curriculum. It is just a sample. You can see here that our course includes engineering disciplines and fundamental disciplines. Actually, according to Russian legislation, all our programs are to be implemented as a part of some general direction. So this program is implemented in the framework of radio engineering, and our students have specific disciplines dedicated to this technique. You can see that algorithms, SDR, and so on. So all this system was very thoroughly discussed and weighted to create the most comfortable environment for the students to get the knowledge of a highly professional type. It is very important to have professional staff. It is exactly understandable. So we have a mixture of foreign lecturers, invited lecturers, and Russian lecturers. In perspective, we are going to use more Russian lectures because all these foreign lectures are rather expensive. However, we do some preparation. For example, for Russian lecturers, we have a special program delivering lectures in English, and they use that, and their level is increasing. Students. We invite students from all the world. Typically, we opened a lot of possibilities for them. For example, at the moment, with the help of national agency Россотрудничество, actually students from all the countries can study in Russia for free. And you can see that we already have students from Colombia, Ecuador, Iran, Mexico, Kazakhstan. They coexisted very well, they became friends, and now we have already several generations of our graduates who were happy with their study. It is very important to create an environment, friendly environment for the students. We did that. We have a lot of opportunities for them to live in Samara and to enjoy their study and their free time. They have a lot of opportunities to visit a lot of sections and a lot of clubs and so on. And they even have their national communities who are eager to help a newcomer, to accommodate, to find his best type of life and so on. So this is actually the last picture. We have a student design bureau. We promote this activity. We encourage our students to show their innovative skill to create their own devices, not obligatory in GNSS area. And this freedom, I think, help them to feel themselves creative people, qualified engineers, and actually it is a part of, I think, good students' life. That's all what I wanted to say. I tried to save time. So if you have any questions, I'm ready.
Could you tell us the prerequisites of the students? Well, what kind of students can you take?
This is a master program, so we expect that our students are bachelor students. I mean, they have a diploma, bachelor diploma, in maybe radio electronics, electric engineering. They should have to know some basics of mathematics, linear algebra. So they should be able to use such software as MATLAB. They should understand basics of electronics, but basics. Actually, our experience shows that we definitely have students of different level. So our first courses include some, courses helping them to make their knowledge more smooth and to prepare for more complicated courses. In the first semester, they have several courses, including even English courses in the English-speaking program, because we know that students from Latin America, for example, typically have poor English. So we try to help them in that.
Thank you so much, Stephen from Uganda. Indeed, I've been working on the GNSS, but for us we use it to help us find out the effects of maybe scintillation or tech in the ionosphere. I'm asking because majority of these GNSS systems, mostly in Africa, are getting malfunctioned, that they work for a short period of time and they collapse. Do you have any future plans when you're called upon to come and work on them such that they can continue working?
Thank you for the question. It's not that easy to answer. However, I would say that at the moment we have significant and substantial constellation of navigational satellites in the sky. These satellites belong to different systems, and one of the tasks maybe is to create a multi-system receiver which is able to process signals of different frequencies, different bands, and to integrate their information into one base. So one of our goals is to encourage students to create their own non-standard positioning solutions. And if we are talking about some regions where maybe GPS or GLONASS or Beidou is not available, fully available, they can try to create something more flexible to use these complex signals, complex information to improve the situation. So it is a challenging topic. However, I can say that this year several students from Latin America choose as a topics receiver of Beidou system, which is actually not available in Latin America, but they were very curious about that, and maybe such curiosity, such complex competencies will play a good role in their career. Repeat, please, for translation.
Короткий вопрос. Этот курс планируется в будущем сделать на русском для простых советских людей?
For Soviet people, it's again challenging. Actually, the program was established by that Professor Bora, who did not speak Russian. And most part of courses at the moment are only in English. Typically, we may discuss that, and if we have, to say, a necessity to do it, if we have many students who want to study it in Russian, we could do it. However, GNSS is essentially international, and it is actually impossible to be a good expert in GNSS if the student is not able to read English literature, English data sheets, and so on. So I think it is the question under discussion. It's controversial. It was the last question. Thank you. The next speaker is Alexander Fedoseev. You are welcome. Please, 10 minutes only.
Hello. Good morning, dear colleagues. My name is Alexander Fedoseev, and I present Samara Enterprise Space Rocket Center progress, well known in the whole world and in Russia as a enterprise of rockets and automatic spacecraft producer. But next I will speak Russian. Ну, помимо указанных направлений, наше предприятие занимается и деятельностью по приему, обработке и распространению информации, получаемых космическими системами разработки нашего предприятия. И в этой связи хотелось бы поделиться опытом и наработками в области применения результатов материалов космической съемки, получаемых нашими космическими аппаратами. Ну, основными потребителями информации дистанционного зондирования Земли на федеральном уровне у нас в Российской Федерации являются прежде всего структуры правительства федерального. Это прежде всего министерства, федеральные агентства, федеральные службы. Говоря о региональном уровне, то наше предприятие, госкорпорация Роскосмос, определено в качестве регионального центра дистанционного зондирования Земли, и возложены на нас функции по приему, обработке и распространению информации, получаемых с космических аппаратов российской орбитальной группировки на территории Самарского региона. Основными потребителями являются структуры и ведомства, входящие в состав нашего регионального правительства. Ну, основными блоками тематических задач являются сельское хозяйство, природопользование, лесное хозяйство, водные ресурсы, городская и транспортная инфраструктура, картография и инфраструктура региональных пространственных данных. Прежде всего, в своей деятельности, в своих работах мы используем данные, получаемые нашими космическими системами разработки предприятия. Это система ресурс П и аппарат АС-2D совместной разработки РКЦ «Прогресс» и Самарского университета. Но помимо этого мы используем открытые данные, получаемыми системами миссии Sentinel, Landsat-8, с датчика MODIS аппаратов Terra и Aqua. В последнее время мы используем данные, получаемые космическим аппаратом АС-2D, так как в нашем центре сосредоточен прием, обработка, управление, планирование и распространение этой информации. Вот на текущем слайде представлено покрытие территории Самарской области в период с мая по сентябрь. Можно видеть, что оно является полным практически сплошным, а некоторые районы покрыты многократно, даже десятки раз. Ну, РКЦ «Прогресс» занимается как созданием и распространением стандартных продуктов, так и тематических, получаемых на основе этих стандартных продуктов. Ну, вообще, как правило, тематическую обработку выполняют организации пользователей информации, которые понимают в специфике предметных областей, но мы тоже этой деятельностью занимаемся. И в дальнейшем я покажу в своей презентации некоторые результаты обработки информации ДЗЗ. Мы пользуемся программными пакетами обработки информации, как нашей собственной разработки, так и коммерческими и общедоступными бесплатными программными комплексами. Мировая практика использования и обработки данных дистанционного зондирования Земли накопила большой перечень вообще тематических задач, которые решаются в интересах потребителя. Создаются специальные классификаторы тематических задач. Поскольку вот в настоящей презентации охватить все задачи достаточно сложно, проблематично и не представляется возможным, то ограничимся 4 крупными блоками использования данных ДЗЗ для социально-экономического развития. Ну, первым направлением является мониторинг водных ресурсов. Существует спектральная зависимость глубины проникновения солнечного света. Отсюда можно построить тематические, батиметрические карты. Технологии мы отрабатывали сначала на авиационных гиперспектральных снимках, и на слайде представлен пример обработки одного из снимков и карта абсолютных глубин с использованием эхолотных измерений. Далее мы эту технологию масштабировали на космические снимки, и здесь представлены результаты обработки материалов космической съемки, покрывающих акваторию реки Волга в Самарской области. Здесь то же самое, но акватория уже океана. В этом же блоке задач можно выделить подблок задач, который посвящен мониторингу ледового покрова в акваториях рек, вот в данном случае федерального значения. Существует зависимость коэффициента отражения снега и льда. И на данном слайде представлен результат обработки гиперспектрального снимка территории Самарской области, акватории Куйбышевского водохранилища. Задача мониторинг ледовой обстановки. Используя гиперспектральные снимки и технологии их обработки, технологии машинного обучения, можно выделить льдины даже. Вот на данном слайде представлен результат обнаружения ледового покрова. Даже вот в частности обнаружена льдина в районе городского пляжа. Это март месяц. Важной задачей и актуальной для таких мегаполисов, как Самара, является мониторинг качества воды в части наличия или отсутствия водорослей. Значит, на слайдах представлены результаты расчета специального спектрального индекса MCI, который характеризует содержание хлорофилла в воде. А здесь представлены результаты обнаружения тоже содержания цианобактерий в воде. Это тоже акватория Куйбышевского водохранилища. На самом деле это актуально для таких мегаполисов, потому что имеет, как Самара, потому что имеет место сбросы сточных вод от промышленных предприятий, и эти воды оказывают влияние на развитие фосфорных и азотных соединений, которые в свою очередь оказывают влияние на цветение водоемов. Следующий блок задач – это мониторинг и оценка состояния объектов, которые подвержены чрезвычайным ситуациям и катастрофам, в том числе и под влиянием деятельности человека. Ну, например, одной из актуальных задач является мониторинг разливов рек в период паводков и наводнений. Здесь представлен результат обработки космических снимков ресурс П на территорию Сибири. Ну, это уже оконтурные результаты в виде векторного слоя. Это маска. Актуальной задачей для территории Российской Федерации с учетом ее значительной территории является мониторинг пожароопасной ситуации, особенно для районов Сибири и Дальнего Востока. Представлены результаты обнаружения очагов пожара. Мониторинг разливов нефтепродуктов является тоже актуальной задачей, особенно она в последнее время неплохо решаться стала с учетом наличия гиперспектральных снимков. Вот на слайде представлен результат обнаружения нефтяного разлива по данным гиперспектральной съемки с учетом априорного знания спектральной характеристики объекта интереса. И дальше мы видим, что действительно объект интереса находится в бухте порта Израиль, и координаты были уточнены по материалам высокодетальной съемки. Следующим блоком задач, актуальным для нашего региона и для соседних регионов, является мониторинг незаконной добычи распространенных полезных ископаемых. Это песок, щебень, глина, например. Ну, на слайде представлена динамика изменений конфигурации и площади добычи полезных ископаемых, вот гипса в данном случае. Черепичная глина. Кроме того, задачей актуальной и востребованной в нашем регионе является мониторинг полигонов твердых бытовых отходов, представленная динамика по годам. Следующим блоком задач является мониторинг транспортной инфраструктуры и городской инфраструктуры. Имея оперативный снимок, строится высокодетальный, строится маска транспортной сети, и затем выделяются объекты автотранспорта, которые подлежат подсчету в автоматическом режиме. Наш регион является регионом, который принимает чемпионат мира по футболу в 2018 году, и в последние годы у нас ведется активное строительство как транспортной, так и в целом городской инфраструктуры. Вот актуальной задачей является мониторинг строительства объектов этой инфраструктуры. По результатам строятся тематические карты классификации и векторные слои, которые впоследствии помещаются и используются в геоинформационных системах. Следующим блоком задач является мониторинг состояния сельскохозяйственных угодий и лесных объектов. Решение таких задач построено на знании того, что состояние растительности характеризуется спектральной кривой. Вот на слайде представлена спектральная кривая, которая меняется в зависимости от степени развития растительности. Существует сотни спектральных индексов, которые рассчитываются по материалам гиперспектральной съемки и которые характеризуют специфические состояния растительности, то есть продуктивность, физическое, биологическое состояние. На слайде представлен результат расчета таких индексов, вот в частности водный индекс, индекс содержания антоцианина и нормализованный разностный вегетационный индекс NDVI, являющийся обобщением состояние растительности. По результатам расчета индексов и дешифрирования и классификации объектов сельского и лесного хозяйства строятся векторные карты и производится выявление изменений. Производится выявление изменений, так называемый change detection. Изменения можно выразить или в пикселях, или в площадях. Ну и, как я уже сказал, результаты тематической обработки помещаются в геоинформационные системы, которые удобны для использования пользователями, организациями специализированными, которые применяют результаты космической деятельности для развития своих направлений. Вот на текущих слайдах представлен пример одной из таких геоинформационных систем по сельскому хозяйству. Разумеется, это далеко не полный перечень тематических задач, которые имеют место и которые актуальны вообще для решения. Но сегодня просто охватить все не представляется возможным, поэтому вот на этом моменте позвольте завершить мое выступление. Спасибо.
Thank you, Alexander. I'm afraid that we have no time for questions, absolutely no. So I would like to invite next speaker, Alexander Ivleev. You have only 10 minutes, please.
Добрый день, уважаемые коллеги. Меня зовут Александр Ивлеев. Я являюсь техническим директором Самарского центра испытаний наноспутников и расскажу вам о его возможностях и услугах. Центр был создан в 2014 году при непосредственной поддержке правительства Самарской области. Этот центр должен был стать производственной базой для реализации научно-образовательных программ университетов, занимающихся выпуском специалистов для космических исследований при создании аппаратов нанокласса. Соответственно, задачи центра состояли в обеспечении выпуска таких аппаратов. Это разработка, макетирование как бортовых систем, так и программного обеспечения. Разработка рабочей документации. Испытания, которые делятся на два типа. Это испытания, подтверждающие безопасность наноспутника для платформы выведения и сопутствующие нагрузки, и испытания, подтверждающие работоспособность наноспутника на всех этапах, то есть транспортировка к месту запуска, запуск и на орбите. Полет по орбите. Подготовка пакета документов для получения лицензии о летной годности. Так. И для реализации этих задач в состав центра входят следующие лаборатории. Значит, лаборатория, которая занимается электронными системами, лаборатория влияния факторов космического пространства, исследования их влияния на наноспутник, лаборатория механических, которая определяет воздействие, вибрации, механических воздействий на системы наноспутника, лаборатория тестирования системы ориентации и стабилизации наноспутника, лаборатория моделирование динамики движения и тестирование датчиков инерциальной информации. Стенд определения моментов инерции и расположения центра масс наноспутников. Также стенд тестирования солнечных панелей и механическая мастерская. Данный центр использовался при создании разрабатываемых в Самарском университете наноспутников. В настоящее время занят испытаниями разрабатываемого блока маневрирования, который будет основой следующего спутника, который получил номинальный Самсат-М. Здесь вот лаборатория создания систем электроники. Она оснащена, вот здесь написано, мы приобрели такой комплекс для полного цикла производства электронных систем. Их тестирование. Здесь показан участок разработки принципиальных схем и топологии печатных плат. Вот на этом, на этом снимке показан участок макетирования электронных систем. Здесь есть паяльная станция, соответственно, там осциллографы, спектрометр, микроскоп. Все необходимое, что позволяет спроектировать и проверить идею на этапе макетирования. Далее здесь показана лаборатория, участок лаборатории, в которой производится автоматизированная сборка электронных узлов. Ну, печатный узел называется. Здесь участок сборки механических и электронных компонентов. Ну, вот здесь лежит такой коврик антистатический, и сборка идет стека электронных. Здесь стоит спутник, в котором сейчас в данный момент собирается кабельная система. Следующая лаборатория определяет влияние факторов космического пространства на работоспособность наноспутника. Это вакуум космический глубокий и температурные циклические нагрузки. Основу составляет камера УП-125ТХД. Она позволяет обеспечить вакуум 10-6 мм ртутного столба, температуру от минус 70 до плюс 200 градусов Цельсия, имеет выход в интернет. Вот здесь показана панель, на которой видно, и также, когда работает, вот особенно на охлаждение, то там двойной компрессор стоит, который до минус 70 позволяет улучшать температуру, то жарко становится вокруг этой камеры, поэтому, значит, удобнее использовать интернет для дистанционного управления, чтобы не подвергаться воздействию жары, которая образуется вокруг нее. Вот здесь термоплита, на которой как раз реализуется температура. Чтобы организовать воздействие разных температур, мы разработали термокожу, в которую помещается наноспутник и устанавливается на термоплиту. И можно цикл по температурам. Дальше. Лаборатория механических воздействий стоит вибростенд ВСВ 202-150. Он позволяет испытывать изделия до 60, массой до 60 килограмм в диапазоне частот от 11,6 до 4000 Гц, достаточно большой амплитудой, и все виды вибрационных воздействий. Синусоидальная вибрация, которая, например, используется для поиска резонансов, вибрация случайная широкого спектра и удары. Для того, чтобы обеспечить испытание, необходимо использовать оснастку. Вот здесь показано несколько видов оснастки. Такая оснастка применяется для испытания отдельных плат и стеков. Такая оснастка применяется для испытания наноспутника, который вот здесь крепление его показано. Либо наноспутника установлено в транспортно-пусковом контейнере. Вот здесь показан ТПК ОАО РКЦ «Прогресс». Внутри стоит наноспутник, и, соответственно, производится испытание, которые должны обеспечить требования предоставления пусковых услуг, чтобы, значит, все было выдержано. Следующая лаборатория – это лаборатория исследования ориентации и стабилизации наноспутника. Здесь используются катушки Гемгольца. Они у нас имеют квадратную форму. Разработчик утверждает, что такие катушки дают более равномерное поле в центре, диаметром примерно полметра. Здесь в середине стоит безмоментный, в кавычках, подвес пневматический, который имеет очень маленький момент трения. До 10 килограмм позволяет повесить на него груз. И здесь вот установлены датчики ориентации. А здесь спутник уже установлен. Такая система снабжена таким имитатором Солнца, простым, на основе галогенной лампы, подвижная система звездного неба и также позволяет моделировать различные виды магнитных воздействий. Также используется это стенд для проверки электромагнитных устройств стабилизации и ориентации. Вот в данном случае вот стандартной компоновки. И также вот мы используем этот стенд для исследования блока маневрирования. Здесь специальная такая насадка спроектирована. Вот здесь стоит блок маневрирования, противовес у него. И, значит, можно мерить тягу и другие интересующие параметры, поскольку мы сейчас заняты как раз разработкой двигательной установки для наноспутника, позволяющей менять орбиту, что очень интересно. Следующий стенд, он позволяет тестировать датчики инерциальной информации, а также имитировать движение. Основу его составляет робот, фанук в виде манипулятора, который дополнен дополнительным программным обеспечением, так называемое бесконечное вращение по оси Z. Вообще говоря, вот это вот запястье робота, оно там изначально позволяет где-то оборот делать только. У нас с новым программным обеспечением около 1000 оборотов можно делать. Вот здесь показаны результаты тестирования датчика угловых скоростей. Ну, робот позволяет до 600 градусов в секунду вращать. Вот если можно запустить. Ну вот просто такой небольшой, если запустится, должен запуститься. Запустилось? Это вот подготовка ведется, когда отрабатывается эксперимент, значит, вот наши сотрудники, значит, устанавливают, смотрят, значит, позиционировать можно либо механически его, либо с помощью лазерной указки, так сказать, точно составить. И точность установки составляет 0,08 миллиметра. И поэтому этот робот также удобно использовать в качестве универсальной координатной установки, такое универсальное координатное устройство. Достаточно. Следующий стенд, это он... Одна минута. Следующий стенд позволяет определять инерциальные характеристики. Здесь вот кино не работает, но он так вот вращается на оси, вот, которая расположена здесь. И по определению периода колебаний с помощью электронных систем, которые делаются, и располагая спутник в разных направлениях с помощью вот разработанной оснастки, можно получить тензор инерции и положение центра масс в строительной системе координат. Также у нас имеется стенд для определения характеристик солнечных панелей. Здесь имитатор используется ЛАМО из 100, который практически точно повторяет спектр Солнца. И располагается этот стенд вместе с роботом. Робот-спутник подводит нужным образом либо отдельно солнечную панель, и можно, так сказать, их характеристики определять стандартные. Здесь представлены перечень услуг, которые может оказать наш центр. Ну, вот 7-я услуга, это, собственно, под ключ можно сделать наноспутник по заданию. И также различные другие комбинации, выполнить испытания и так далее. Кроме того, наш центр может быть использован при организации программ обучения в Самарском университете. Спасибо за внимание.
Thank you, Alexander. I think all the questions could be asked during the coffee break, and we have one important message from organizers. Today, in the afternoon, in the evening, we have a social program, and organizers ask all of you to come to the registration board just during this coffee break and confirm your participants, if any, in this activity. Is it clear? So please come to the registration board, to the organizers, and confirm your participants, or maybe you're unwilling to go there. So don't forget that our next session will start at 11.
Yeah, and there is another announcement. As I mentioned yesterday evening, we will split after lunch in working groups. So these 3 rooms will be divided, and there will be a sign-up sheet at a registration desk for each of the working groups. So please do not forget to pass by before the end of the lunch break and sign up to which working groups you would like to participate. So working group 1, as I mentioned yesterday, I mentioned the topics already of the working groups yesterday. So we wanted to just announce also who will be chairing the working group, so just that you are aware. Also, some of you might have not heard about your roles in this. So the working group 1 on space economy, that will be chaired by Viktor Taratukin, and then the rapporteur will be our colleague from, I think Arthur C. Clarke Institute. Then Space Society, here we talk about role of universities, public sector. The chair, well, I would say rather moderator will be our colleague from Professor Michael Magraf from the UAE, and then Viktor Lagutov will be helping as rapporteur. And then the working group 3, space accessibility, I think you will be moderating that group. You do? Okay.
I have my own report and my assistant.
Oh, okay, good. Well, we kind of thought of someone to assign to you too, but if you have it already, you will have to. Okay. So these are the chairs. Again, just check the topics and try to sign up. Make sure that, there are not 50 people in one group and 10 in the other, of course. But hopefully we will have the list so that you can already join the right groups in the afternoon. Okay, thank you.